So we're going to work through a beautiful exam. This is from spring 2024, Calculus 2, locally known as 166, now 1660. The third exam, which means we're talking sequences and series. We're going to have a blast. But of course, before we can begin, right, we always need to put our name on it. Because after all, if we don't put our name, well, we're not going to get the credit. All right, let's go. Our first problem. Determine whether the series below converge, because there's two of them. In each case, you should clearly indicate the test you are using, state the conclusion of the test, and clearly justify the steps needed to reach this conclusion. All right. Well, the nice thing is these look fairly independent of each other, so that's going to make our job straightforward. And what do we see right away in part A? We see a exclamation mark, and that means factorial. When we think factorial, we say ratio test. So here's our idea. We're going to apply the ratio test. Now, we'll go through this and work it out in a second, but just as a reminder, C factorial, you should always think ratio test. Now, what's going on? Well, you should think of this whole thing here as A sub n. And we want to compute what we call rho, which is the limit as n goes to infinity of an plus 1 over an. Now, we can put absolute values here. They don't make any difference because everything's positive. This is a very optimistic summation here. All right, so we need to put these in. Now, remember when you're doing limits, be consistent with writing limits, because some people are very persnickety, if you will, about that. Now, how do we do an plus 1? Well, we're going to come here, and everywhere where we see an n, we put an n plus 1. Here, parentheses can be your friend. So 2 times n plus 1 factorial. Divide by 3 to the n plus 1 times n plus 1 factorial squared. Okay, now we're going to divide by an, which is the same as multiplying by the flipped version. So 3 to the n factorial squared. Divide by 2n factorial. Cool. Now, we want to get to the point where we get lots of beautiful cancellation, because we always love beautiful cancellation. And so for factorials, sort of our mindset here is to say, let's get these to somewhat cancel. Because what do you have up here? Well, you really have 2n plus 2 factorial. And that's not so different from 2n factorial. How different is it? Well, if you think of what 2n plus 2 factorial is, it's 2n plus 2 times 2n plus 1 times 2n minus 1 times n. So most of it is 2n factorial. It's just there's some extra terms at the front. So the idea is pull off some terms. All right, so let's write down what we have. We're going to say this is the limit. As n goes to infinity, we're going to have 2n plus 2, 2n plus 1. I keep pulling until I hit what I'm going to cancel with, and then I switch to factorials. Downstairs at 3 to the n plus 1, I'm going to take advantage of that plus and say that's really 3 to the n, 3 to the 1. This n plus 1 factorial, I'm going to again pull off an n plus 1, and then I have n factorial. So that gets me ready to get some cancellation going. 3 to the n factorial squared, and 2n factorial. And if we've lived a good, clean algebra life, good things will happen. This 3 to the n cancels, this 2n factorial cancels, this n factorial being squared cancels with this n factorial being squared. Oh, nice. And well, what do we really see here? Well, we can say this is limit as n goes to infinity. Now, here, I'll go ahead and factor an n out of these terms, because what's really left? Just this part, the 3, n plus 1 factorial squared. And so, I'll go ahead and pull an n out twice, so n squared, 2 plus 2 over n, times 2 plus 1 over n, divide by, here I'm going to pull an n squared out, times 3 times 1 plus 1 over n, quantity squared. Now, if you don't want to pull out that end, that's perfectly fine. The punchline here is at this stage you've got polynomial over polynomial. Life is good. And you just look at your leading coefficients. This is just, hey, whoa, slow down, apply the brakes. And what do we see? Upstairs, well, the 2 over n, the 1 over n goes to 0. So we have 2 times 2, which is 4. Downstairs, we have 3 times 1 squared, which is 3, 4/3. Now, what's true about 4/3? 4/3 is bigger than 1. Well, what does that mean? So, diverges. So what you're doing is when you're applying the ratio test, you compute this limit. If it's bigger than 1, diverges. If it's less than 1, converges. And we're done with part A. That took a minute. Let's hope part B goes a little faster. All right, so what do we have here? We have a sum, n, 2 plus 1 over n, divided by 3 to the nth power. Now, since we just did ratio tests, we're kind of in that mindset, ratio and root, they kind of go together, and this one is a beautiful one to do root test. See that nth power? That's going to become super clean when we do an nth power, or sorry, an nth root. So here's the idea. We're going to apply the root test. All right. And so again, we're thinking of this whole thing here as a sub n, and we have this similar term, rho. But now it's the limit as n goes to infinity, absolute value of a n to the 1 over n. Well, that's the limit as n goes to infinity of n, 2 plus 1 over n over 3 to the nth power to the 1 over n. Well, that's the limit. And now what we can do is we can distribute it in some sense, this 1 over nth power. N to the 1 over n, and then we have 2 plus 1 over n over 3 to the n to the 1 over n. Well, that last term is going to be pretty simple. So why? N to the 1 over n, they cancel. So we have really 2 plus 1 over n over 3. All right, now what's going to happen? Well, n to the 1 over n, classic limit. This goes to 1. And now this 1 over n goes away. This goes to 2/3. So what do we see? Altogether, we see, lo and behold, that rho is equal to 2/3. Now, what's true about 2/3? Less than 1. And so this converges. All right, because that's what we need to see. We need to see, does this converge or not, right? That's our goal. Read the instructions. Determine if they converge. So not converge is diverge. And we showed our steps. We stated our conclusion. We did our justification. We're good. Whew. Okay, that one took a lot of time, but that's okay. We're moving along. Number 2. For each series and test, okay, so it tells us the test, do the following. Choose an appropriate comparison series. Okay, we can do that. State and justify the convergence behavior of your choice. Okay, cool, we can do that. Perform the indicated comparison test showing all steps, and then state the convergence behavior of the problems series and explain how your answer is justified by the test. Okay, there's a lot of things here to do. Let's just go through and carefully work our way through this, all right? No stress, no pressure, just work through it. Okay, so we have n plus 3 over n squared minus n. Now, with practice, we'll get to the point where we can almost look at a series and say, I know what's going to happen. Now, how do we get to that point? Lots of practice, that's what I said. But in things where there's plus and minuses, you just sort of say, pay attention to the big terms. Big term upstairs, big term downstairs. Looks like you have n over n squared, that's like 1 over n. 1 over n is harmonic, diverges, and we're done. And that's almost what we're going to do. It's that quick. Okay, so now, have an appropriate comparison series. Now, when you're doing a direct comparison test, you have to kind of know ahead of time what you think the answer is. Do we think this converges or diverges? Because depending on the answer, then we are going to do something different. Okay, so what do I mean here? Well, if I'm thinking that this is something which converges, I want to get something above it which converges. If I think it's something which diverges, I want to get something below it which diverges. So I said, I think it looks like 1 over n. So I said, okay, I want to get something that kind of feels like 1 over n that's below this. And so I kind of, this is weird to talk about because it's like I'm doing the problem before I do the problem. But it's one of those things that happens. And so I say, can I make this bigger than 1 over n? Or is it bigger than 1 over n? And I think it is. Okay, so here's my guess. I'm going to say, I'm going to compare with the sum, and it doesn't really matter where we start, so we'll go ahead and start at 2 to infinity, 1 over n. Okay, now, what do we know about this sum? This diverges. Whoops, diverges, I can spell that, because it's harmonic. And so that's always in our back pocket, ready for us to pull out harmonic sum, classic sum. Okay, so we did step 1 and 2. Step 3. Now here's where I said you have to be careful, right? Because you have to get it just right. So the question is, did we make the right choice with this 1 over n? Well, we can if we say 1 over n is below what we want. Because if we want to show something diverges, we got to put something below it. If we want to show something converges, we want to put something above it. So we said, it's got to be below. Now, why is this true? Well, if you look, we say denominator, I point to numerator. Numerator is bigger than n. And now downstairs, denominator is smaller than n squared. Now, why am I saying all of this? Well, how do I make something smaller? I make the top smaller, I make the bottom bigger. And so you'll notice by removing the plus 3, then what I can really say, let's go ahead and add an intermediate step. 1 over n equals n over n squared. And n is smaller than n plus 3, so that makes the top bigger. N squared is smaller than n squared minus. That makes the bottom smaller, so it's true that the whole thing is bigger. Okay, so that's 3. All right, so last thing, 4. So the sum that we want to look at, n plus 3 or n squared minus n, converges by direct comparison test. There's a lot to write down on the third exam. But the ideas aren't that bad. So don't get intimidated by writing. So this, not converges, diverges. It would help if I did my work. It diverges by direct comparison test with the sum of 1 over n, and that's the work that we have to show. All right. B. 2n over 4n minus 3, limit comparison test. Oh, I love limit comparison test. I am a huge fan. Now, I like to think of limit comparison test in the following sort of phrase. I like to think of it as you get rid of the noise. And you might say, well, what does that mean, get rid of noise? Noise is lower order terms. In other words, focus on what's really driving the behavior. It's going to 0, but how is it going to 0? What's making it go to 0? And so when we do this kind of thing, what we do is we look at the downstairs and the upstairs. And so we'll do it on the side here, then we'll work through our process. And we say, all right, there's multiple terms being added and subtracted. There is downstairs. Upstairs, no, there's no choice, so we're going to stick with the 2n is what's causing the upstairs to be upstairs. Downstairs, 4n minus 3. I have 4n. I have 3. Which one dominates, the 4n or the 3? Well, the 4n is getting huge and the 3 is still very 3. So the 4n is dominating the behavior. So it says, hey, ignore the 3. So really, this says, look, this is behaving like 2n, 4 to n, or 1/2 to the n power. Okay, so that's the idea. Now, let's go through our steps, step by step. All right, step 1, we have to say, what are we comparing it to? Well, that's what we did over here. So compare with our summation n equals 1 to infinity of 1/2 to the n. Now, what do we know about this series? This series converges because, why? It's geometric. It's geometric. And not only is it geometric, we can say, well, look, the absolute value of r is equal to 1/2, right? That's what we're multiplying by each time, and that's less than 1. So when you have something that you're multiplying each time that's small, it converges. If you have something multiplying each time that's big, diverges. And small and big are smaller than 1, bigger than 1. All right, now, what do we need to do here? How do we justify? Well, we take the limit as n goes to infinity of 2n over 4 to the n minus 3 divide by 1/2 to the n. Well, if you take a look at this limit, that's limit as n goes to infinity, you can multiply that 2 to the n up. It's really 4 to the n over 4 to the n minus 3. And now, if you divide by the growth, which is, say, 4 to the n, that's 1 over 1 minus 3 over 4 to the n, and that's equal to 1. Now, when we're doing limit comparison test, we don't care about it being 1 or smaller than 1 or bigger than 1. We just want a number. We almost always get one by the way we construct it. So don't be surprised in limit comparison tests that you get a 1. And really what that says is like, you nailed it. You really captured the essence of how this is going to 0. And so we say, okay, what's our conclusion? That's step 4. We say, look, the sum that we were looking at, 1 to infinity, 2 to the n, over 4n minus 3, will converge by our limit comparison test, and with this sum 1 to infinity of 1/2 to the n, and because this limit is 1 and that sum converges. So like everything that justifies it was done in steps 2 and 3. Oh my gosh, these problems are taking a while. Well, there's a lot to do. There's lots of small things to check, but keep going. Be consistent. There's no need to run. Don't panic. Breathe in. Breathe out. It is a warm summer day. We are taking a test. We are in our happy place. All right, let's look at number 3. Consider the series. So it's the sum 1 to infinity n e to the negative n. Step part A. State the 3 required conditions for the use of the integral test. So, okay. Now, I would say there's some mild controversy about this, but the main thing, the absolute main thing, you really ultimately, if you satisfy this, everything else follows. It's a little bit technical about why, but you need it to be decreasing. All right, so that's the main thing. The other things that we really are looking for, non-negative, but you could also say positive. And that just says we don't want to go down below 0. And the last thing is you want it to be integrable, or you could say it's continuous, something that says, oh, I actually can integrate this. You know, that's the kind of thing you're looking for. So those are the 3 categories. It's decreasing, it's never negative, I can integrate it. All right, so those are the main things we say. But ultimately, if you leave out decreasing, you should lose like 2 out of 3. if not 3 out of 3, because that's the ultimate one. Okay, so part B. I was going to say step B. Use the integral test to determine the convergence of the series, and I took it off the screen, so let me pull it back down. It's the n e to the minus n. Providing justification as to why the series converges or diverges, you may assume that the series satisfies the requirements for the test. Okay, so we don't have to do the following. We can say, look, it's decreasing, it's non-negative, it's integrable. Okay, so we have that. Now, here's the idea. We say that the sum that we're after, 1 to infinity and e to negative n, converges if and only if the integral 1 to infinity x e to negative x dx converges. Okay, that's the integral test. It says if you satisfy the requirements, you can jump back and forth between a sum and an integral. Now, we need to figure out this integral. All right, so, so this is really an integration problem. Good. We love integration, don't we? All right, x e to the negative x. How does one integrate that? Well, we would do the following. That would be integration by parts. So we're going to let u be the x and the dv e to the minus x. So that would make du as dx and v is minus e to the minus x. So we have uv minus x e to the minus x. And then we're going to evaluate that from 1 to infinity. We'll compute that in a second. Subtract the integral v du. Now notice there's already a minus there. Minus minus makes a plus. Integral 1 to infinity e to the minus x dx. Okay, so this is minus x e to the minus x. Evaluate from 1 to infinity. And then here it's minus e to the minus x. Evaluate 1 to infinity. Now, when you plug in 1, that's not so hard. So that's the easy part. It's the infinity that's the hard part. What makes that hard? Well, the problem here, when you plug infinity in the second part, no worries. But when you plug infinity into this first part, you see that part gets huge, but that part gets small. So what happens overall? Now you could say, oh, I know that polynomial versus exponential, I know which one is bigger, and that tells me the answer, which is good. If you know that, beautiful. If you don't know that, well, you got to do some work. So let's go ahead and be super careful. So this is an improper integral because it involves infinity. So if we're being super careful, because they didn't tell us how careful we had to be, right? They said provide justification. So we would say, well, this is the limit as x goes to infinity of minus x e to the minus x, which is minus x over e to the x. Okay, that's when you plug in the infinity part. That's really what it means. When you plug in infinity, it says, well, what happens as you get big? When you plug in 1, you get minus makes a plus 1 over e. Here, when you plug in infinity, e to the minus infinity is 0, so we're not even going to think about that. And when you plug in 1, again, it's minus 1 over e. Minus makes a plus. Now, what do we do here? Yes, it goes to big over big. Infinity over infinity. So, le hôpital, mon ami. Yes. We will do it. Just when you thought the le hôpital was gone, it pulls us back in. And so we take the root of the top, root of the bottom, and then we say, oh my goodness, now what's going on? Well, we have e to the x downstairs, a minus 1 upstairs, and everything else is 2 over e. This part goes to 0, and so we end up with 2 over e. Now, the number doesn't matter. The fact that it's 2 over e, we don't care that much. What we care about is it finite or not? And it's finite. So we got an answer. That tells us the integral converges. So now our conclusion, since the integral converges, because that's the work here, right? That getting a number means converge. So since this converges, then this must converge. Then our sum, n e to the minus n, also converges. And that's it. That's the integral test. It basically says, hey, turn your sum into an integral and carry it out. All right, more than halfway. No, halfway. Okay, halfway. But we haven't used up half our time, so we're doing okay. We're doing okay. We're not stressed. We are calm. Number 4, find the interval of convergence for the power series below. Carefully justify your reasoning and indicate the convergence test you use. Okay, so when we talk about interval of convergence, we're really saying for which x is this true. And now, almost always, in other words, always, we're going to start by using one of two tests, ratio or root. And the rule of thumb is, as much as possible, use the root test. Root test is going to be a simpler test. If you have factorials, or occasionally if you see lots of plus signs, then you might shoot for ratio, but in general, root test is where it's at. Okay, so we're going to channel our inner root test mentality. So we look at this and say, let's think of this thing right here. We'll call it a sub n. And we're going to start by saying, what's the limit as n goes to infinity of absolute value of an to the 1 over n power? Well, okay, so that's the limit as n goes to infinity of, now when we take the absolute value, the only thing absolute value will affect is this x minus 10. That's the only thing that could be negative. So we're going to have 2 to the n, absolute value x minus 10 to the n, over n to the 1/3 to the 1 over n. Now, we'll go ahead and distribute this 1 over n through, and when I say that, it just means every piece gets a 1 over nth power. So it's 2 to the n to the 1 over n, absolute value of x minus 10 to the n to the 1 over n to the 1/3 to the 1 over n. Now, good news, n to the 1 over n simplifies really clean. So this becomes the limit, n goes to infinity. We're going to have 2 absolute value of x minus 10. Now, here's another beautiful thing. If you see something to a power, you can swap the order of the powers. So think of this as n to the 1 over n to the 1/3. Now, why do that? Well, there's a nice fact. N to the 1 over n does what? It goes to 1. And that's the only place n show up. Yes! So, the punchline. This becomes 2 absolute value of x minus 10. Now, we're doing the root test. So since we're doing the root test, what do we want? Well, we want this to be smaller than 1. Or we could say, look, we want absolute value of x minus 10 to be less than a half. Now, that's another way to say negative 1/2 less than x minus 10 less than positive a half. And if you add 10, you get 10 minus a half. Well, we can say that's 9.5 less than x less than 10.5. So picture-wise, what's happened here is 10 is our center, and we can get that from seeing x minus 10. And now we're going to go out 1/2 in each direction. And at this stage, we have these numbers, 9.5, 10.5. And here's what we know so far. In between 9.5 and 10.5, life is good. We definitely converge. Outside of 9.5 and 10.5, we know we definitely diverge, which means that we've gotten all but 2 points determined whether it converges or diverges. So most of the work has been done. Once you found the radius, you found all but 2 points. But we're not after radius. It really emphasized interval, so we're not done until we know the story about 9.5 and 10.5. So here we go. Let's talk about that story. So at x equals 9.5. So we'll start there. We plug it in. So this becomes the sum, 1 to infinity, 2 to the n, 9.5 minus 10 to the n, over n to the 1/3. Now, 9.5 minus 10 is minus a half. So we can say, hey, that's the sum, 1 to infinity, 2 to the n, minus a half to the n, over n to the 1/3. Or, if we just multiply 2 times negative a half, we say, well, wait, that looks like minus 1 to the n over n to the 1/3. And we're like, yeah, we love a good minus sign. Why? Well, because when we see a minus sign, there's a beautiful test, and it boils down to a simple question. Do you decrease to 0 or not? If you don't decrease to 0, okay, forget it, hopeless. If you do decrease to 0, you converge. And so now we say, well, what's happening with this 1 over n to the 1/3? And we say, that's going to 0. So we say, since 1 over n to the 1/3 decreases to 0 by alternating series test, we converge because we decrease to 0 and we're alternating our sign. So that tells us what? It tells us 9.5 made the cut. It's in. So we're going to shade it. It got in. 9.5, we like it. Now, 10.5, okay, we got to repeat and see what happens there. Sometimes they're both in, sometimes they're both out, sometimes it's just one. So you don't know before you do the check. So we have 2 to the n, 10.5 minus 10 to the n over n to the 1/3. Now here it's very similar, except 10.5 minus 10, positive a half, not negative a half. So we're going to get 2 to the n, 1/2 to the n over n to the 1/3. And that means we're going to get sum 1 to infinity of 1 over n to the 1/3. Now, what is this? This is a p-series. So this is a p-series. And a p-series means what? 1 over n to a power. So p is the power. With p equals 1/3. Now, here's the thing. P-series converge if and only if we're above 1. This is less than or equal to 1, so diverges. All right, so we know it's a p-series at that point, so it's diverging, which means 10.5 is out. So we shade it in with the red. All right, so put it all together. We have that our interval of convergence is 9.5 less than or equal to x less than 10.5. Now, some people prefer other notation. So if you prefer 9.5 with bracket, comma, 10.5 with the parenthesis, we are smart enough as graders to know, yes, that means the same thing. Just the important thing is you have the right answer, and it's a clear common convention. All right, well, before I leave it, I just want to say, interval of convergence, if there's any question you could bet on interval of convergence. It's just, they always put it on. The reason is because it tests a lot of very important concepts. You test ratio root test, you do some good manipulations, you have to test the endpoints. It's just classic. So know your interval of convergence problems. Start with your ratio root, figure out your radius, make sure you rearrange it. So you say, where does x go between? Get it down to 2 points, test those 2 points, put it all together. Life is good. You get the points and you walk out of that exam knowing, I got it right. All right. Number 5. Consider the series. We have the sum 1 to infinity minus 1 to the k over k plus cosine pi k over k plus 1. Okay, before we do anything, they're trying to be sneaky here. If you ever see a cosine pi k, they're just saying, hey, we're trying to obfuscate. Secretly, this is trying to behave like another minus 1 to the k. So this is 1 to infinity of minus 1 to the k over k plus minus 1 to the k over k plus 1. Okay? All right. That's just going to be easier for us to write down. So see a cosine pi k, write it with what it really is. All right. Find the sum of the first 100 terms. And your answer should be an integer or a fully reduced fraction. Now, we're not literally going to add 100 things together. That just doesn't seem reasonable. And mathematicians, believe it or not, are reasonable people. And so we say, okay, so we know that they're reasonable people. So what's going to be happening here? Well, we can tell it's not geometric because this k is not an exponent. So it's like, okay, so it's not geometric. So we suspect telescoping. So we're going to write down a couple of terms until we spot the pattern. And once we spot the pattern, then we'll go on from there. Okay, so here we go. Let's start with 1. So at 1, we're going to get minus 1 over 1 minus 1 over 2, right? Because when k equals 1, minus 1 to the 1 power is a minus. Plus, now we're at k equals 2, minus 1 to the 2 is a plus 1. So you get a 1 over 2 and a 1 over 3. Plus, now we'll go to the next term. Well, we're going to get a minus 1 cubed, that's a minus, so minus 1 over 3 and a minus 1 over 4. Okay, let's go ahead and do one more. Plus, and okay, so now we're at 4. Minus 1 to the 4 is a plus, so it's 1 over 4 and plus 1 over 5. Okay, and then it's going to keep going, and then we're going to get to the end. Okay, so n was 100. Okay, so what's minus 1 to the 100? Well, that's going to be 1 over 100, because minus 1 to 100 is a plus, and then it's going to be a plus, and minus 1 to the 100 over 101, so 1 over 101. Okay, all right, so that's where we're at. Now, what do we see? And I think we probably spotted this pretty quickly, right? You see how we get minus a half plus a half? Okay, cool. Those cancel. Plus a third minus a third. Great. Those cancel. Plus minus a fourth plus a fourth. Those cancel. So we're getting these beautiful cancellations going. And so this is going to cancel with what comes next. Lots of cancellation happening in the middle. And now this 1 over 100 is going to cancel with what came before. So that's gone. What's left? Well, we have this term at the start and that term at the end. Okay, so we are left with a minus 1 plus 1 over 101. All right. Now, unfortunately, we can't stop there because it says your answer should be an integer or fully reduced fraction, which means you gotta push it all together. Well, common denominator would be 101, so this is minus 101 over 101 plus 1 over 101. And, well, that's going to be minus 100 over 101. And so there's the fully reduced fraction. Now, part B. Find an expression for the sum of the first n terms. And your answer should be an expression involving n. Well, it's going to be the same thing, right? We're just going to start. And so we'll write down just a little bit here at the beginning. The only thing that changes is where we stop. And we're going to say, well, the first n term, so we're going to stop when k equals n. So we have minus 1 to the n over n plus another minus 1 to the n over n plus 1. And again, cancellation, telescoping. There's not a lot of things that we can actually find the value for, And so when they ask us to find a value, we know what's going to happen. So almost everything cancels except a little bit at the beginning and a matching little bit at the end. So in essence, it's kind of like a mirror. So whatever doesn't cancel at the beginning, if you were to reflect, that'll mirror what doesn't cancel at the end. So what's left? Well, we have minus 1 plus negative 1 to the n over n plus 1. Okay, that's part B. And part C, find the value that the series converges to by finding the limit. Oh, so we say, okay, so it's the limit as n goes to infinity of negative 1 plus negative 1 to the n over n plus 1. And now we say, well, hey, this is going to either plus or minus 1, but this is getting huge. And so our answer is negative 1. And there we go. Huh. Whew. You know, this feels good. That's sort of a nice cool down after some of the ones we've been doing. All right, so that brings us to number 6, our final problem on this exam. All right, so consider the function f of x is x e to the 2x. Part A. Find p2 of x, the Taylor polynomial of order 2, centered at 0 for f of x. Okay, so there's a couple of things we need to do. We need to know where we're at, and so we're centered at 0. We need to know what our order is. Now, that's also given 2 places, right? P sub 2, and then explicitly said order 2. Now, order 2 means we're working up through second derivative. Okay, so here we go. Now, we're going to do the following. We have our function, and so we need to find our function, our first derivative, so product rule. Derivative of the first is 1 times the second, plus the first, x, times the derivative of the second, which will bring in a 2 down. And then we're going to do another derivative. So that's 2e to the 2x, plus derivative of the first, 2e to the 2x, plus derivative of e to the 2x will be a 2 down, 4x e to the 2x. Okay, so second order, work through second derivative. The order refers to what derivatives you need to look at. Now, after you've taken our derivatives, we need numbers. So we're going to take these, and we're going to now plug in at the center. So we're going to plug in what is f of 0, what is f prime of 0, what is f double prime of 0. So f of 0, 0 times 1. That's 0, okay? 1 plus 2 times 0 times 1. Well, that's 1. Okay, not super exciting, but that's all right. And then we're going to have 2 and 2 and 0. That makes 4. So we have 0, 1, 4. Now, our moment of truth. What is P2 of x? Well, it is the following. So P2 of x, and since we're centered at 0, I'm just going to put it at 0. That's going to be f of 0 plus f prime of 0 divided by 1 factorial, which usually we don't write down, but we could. So, heck, why not? We'll go ahead and write it down. It's divided by 0 factorial, divided by 1 factorial, and it'd be x minus 0 to the 1, and then it'd be f double prime of 0 over 2 factorial x minus 0 squared. Well, that becomes 0. All right, that doesn't do anything. 1 times x, which is x. 4 over 2 is 2x squared. So our function is behaving like x plus 2x squared. And there we go. There we go. All right. Now, part B. Show that for all x between 0 and a fourth, we have that R2 of x is less than or equal to 7 over 96, where R2 of x is the error for the Taylor approximation. For the purposes of estimation, you should use that e is less than 4. Actually, E is about 2.71828, so it's less than 3, definitely less than 4, but okay, we'll roll with it. That's fine. If you say 4, we're on board with you. So then we have the inequality, may be of use. Well, yeah, that's the error approximation. It will be of use. All right, so if we're trying to approximate, or say how bad we are in our approximation, really, for P2, we need to look at the next derivative. So the error from the second order Taylor polynomial will be driven by the third order derivative. So step 1 is we need to find the third derivative. So here we go. We have our second derivative. So we'll write that again. F double prime of x, that's 4e to the 2x plus 4x e to the 2x. So F triple prime of x, all right, so 4 times 2 makes 8e to the 2x plus, rid of the first, well, that'll be 4e to the 2x, and then plus, we're going to have 4x e to the 2x where the 2 comes down, and so that's going to become an 8x e to the 2x. Or that is 12e to the 2x plus 8x e to the 2x. Okay, now, what do we need? Well, we need to understand, what is this m? They didn't tell us that. And by the way, this should have been an absolute value, but we'll forgive them. We'll forgive them. That's okay. We're amongst friends. We're nice people. What is this m? Now this m is, and the reason we did all of this is how bad this next derivative could get. So it's the max of the n plus first derivative of y, where y is between x and the center, c. Okay, so here's our third derivative, and we are interested in between 0 and 1/4. So, thinking about this, notice e only gets bigger as we let x get bigger. X only gets bigger as we let x get bigger. So the max, m, which is this max of f triple prime of y, where we're between 0 and 1/4, well, and technically there's an absolute value here, and I forgot to put it here, so let me put it here. Everything's positive, so we just plug in 1/4. And so that's 12e 2 times 1/4 is 1/2, and plus 8 times 1/4 e to the 2 times 1/4 is 1/2. Now, you might have noticed something. They said, hey, e is less than 4. Okay, so let's use that. So this is less than 12 times 4 to the 1/2. 8 times 4 is also known as 2 times 4 to the 1/2. 4 to the 1/2, secret code for 2. So this is less than 12 times 2 makes 24. And 2 times 2, that makes 8. 2 times 2 makes 4. I can do that. And 24 plus 4 is 24 plus 4. I'm getting ahead of myself because I see where the computation is going. That is 28. Okay. All right. How are we doing? So far, so good? All right. Well, we're almost there. We're in the home stretch. So, now, what can we say? So, we can say that our R2 of x is going to be less than or equal to our 28. That's our bound we got from m, using that e is less than 4. And now, times x minus c. Well, again, I'm in between 0 and 1/4. Okay, so how big should I get? Well, the biggest I should get is 1/4 minus 0. Right? That's the biggest I can get in this interval. 2, what power? N equals 2, so 2 plus 1 makes 3. Divide by, and 2 plus 1 factorial. Okay, so everything else from here is simplifying. So what do we have? We have really 28 and a quarter cubed. That's really 4 cubed downstairs. And then we have this 3 factorial. Well, okay, 28, that's 4 times 7. Then this 4 cubed is 4 times 16 times 6. 3 factorial is 6. The 4's cancel. And then what do we see? Well, we see 7 upstairs, and 16 times 6 is 96. Exactly what we have. So we were asked to show that our error is bounded by 7 over 96, and that's the work. Now, the main part of this is really getting a handle on m. Once you know m, all the other pieces, there's not much you can do. You just say, okay, how big do you get from the center? Raise that to the right power, divide by the right factorial. And so it's the m. That's where you have to put your effort in and make sure you understand what's going on. Whew! Wow, what a test. But we finished it. We finished it with plenty of time left that we could go back and check our works. The third exam in Calc 2 is often one of the more challenging exams you will face. Not because the math is necessarily hard, but there's a lot of concepts, and now there's a lot of justifying that has to go on. And things like error approximation is kind of a different animal in some sense, and one we're not quite as used to, but still one that's really useful. Keep putting in the work. You can do this. I believe in you. You're wonderful. Thank you for joining me. Put in the time. You'll be great. All right. Take care. Bye.